Hello, AI enthusiasts. Welcome to our deep dive into decision trees. Building on our previous talk about k-nearest neighbors, where we classified data by looking at nearby points, most tutorials never tell you how a model can think like a human strategist. In this video, we want to show something different, the elegant branching logic that mimics a game of strategy to find the perfect answer. Think of it like a game of 20 questions. You are trying to guess a secret object. Instead of guessing randomly, you ask a series of yes or no questions to narrow down the possibilities. Each answer splits the world into two groups, the items that fit the description and those that do not. This is exactly how a decision tree operates on data. In a dataset, a question looks like a physical boundary. If we are classifying fruit, our first question might be, is the weight greater than 100 grams? This single question slices our data space in half. On one side, we have mostly one class, but on the other, we still have a mixture that needs more investigation. This process is recursive, meaning it repeats on every new branch. If the first split did not give us a clear answer, we ask a second question, and then a third. Visually, we are carving the data space into smaller and smaller boxes. Each box represents a leaf in our tree. But how does the model choose the right question? It looks for the split that makes the resulting groups as pure as possible. Just like in our game, you would not ask if an object is blue if half of all things in the world are blue. You want the question that provides the most clarity and separates the classes most effectively. The depth of the tree determines its level of detail. A shallow tree might only identify broad categories, while a very deep tree creates highly specific rules. Imagine a tree so deep, it has a unique branch for every single data point it has ever seen. This is like a tailor making a suit that only fits one specific person's exact posture. If the tree is too deep, it learns the noise and quirks of the training data rather than the general patterns. When it meets a new data point, it fails because its rules are too narrow. We call this overfitting. To make a prediction, a new data point simply follows the path from the root to a leaf. At each junction, it answers a question based on its own features. Once it reaches the end, the leaf node tells it which class it belongs to. This makes them easy to interpret. Comparing this to our previous look at k-nearest neighbors, the differences are clear. While KNN creates fluid, organic boundaries, decision trees create rigid, rectangular regions based on rules. Each approach has its strengths, but the tree's ability to explain its reasoning is a massive advantage. In the real world, you see these trees everywhere, from credit scoring to medical diagnosis. A bank might use a tree to decide if you qualify for a loan by asking about your income and history. Because every path is a series of logical steps, it is easy for a human to audit the decision. Decision trees turn complex data into a simple game of strategy. By recursively splitting the world into smaller, purer groups, they provide a transparent and powerful way to make predictions. If you found this look into rule-based learning helpful, stay tuned as we explore how combining many trees can create even more powerful models. See you in the next deep dive. Subscribe for more insights into how algorithms make logical decisions.